Okay, remember that our goal is not to approximate it, but which would mean like square root it on a calculator and make it a decimal. Our goal is to keep it exact like it is. So square root of 30 is exactly square root of 30. So keep it that way, but simplify it out if possible. Square root of 30, we're looking for factors. Let me make a list over here. So 4, 9, 16, 25, 36, 49, 64, 81, 100, and it keeps going, but for now we'll just leave that. We're looking to see if any of those go into the number. If not, like 30, then it's already simplified. In other words, 4 doesn't go in, neither does 9, and then 16 is already past halfway of 30, and if we divided it 30 by 16, we would end up with the decimal, which we're not doing. So this one is already simplified. Okay, how about 18? Just go through this list every time. That would be my suggestion if you're struggling with this. So, and the list I'm talking about is over here. So does 4 go into 18? Nice and neatly. No. Does 9 go into 18? Yeah. So we'll do square root of 9 times square root of 2. So we split it up into the factor that can be nicely square rooted, and then the other one, there's the leftovers. Okay, what's the square root of 9? Okay, so that one, the square root of 9 becomes 3. Don't put the square root still on there. So in other words, sometimes students will leave that square root. Don't do that. It's wrong. We already did the square root. And then the square root of 2, we just leave alone. So 3 square root of 2, that's the simplified radical form of square root of 18. Okay, 12, we, again, just go through your list. Does 4 go into 12? Yep. So we'll split this up into square root of 4 times square root of 3. And then we square root the nice one, the nice neat one. What's the square root of 4? 2. Thanks. Okay. Leave the square root of 3, that ugly, messy one, alone. You good back there? How about 108? Well, does 4 go in? Yes, but it seems like with this one we could probably get a little bigger number. And remember, that saves you some work. So does 9 go into 108? Yeah, it does. Does 16? No. 25? Definitely not. Does 36? Actually, yeah, it does. So if you can, like, the biggest number you can use is better because you don't have to do multiple steps that way. Okay? So this is square root of 36 times square root of 3. And then square root of 36 becomes 9. Leave the square root of 3 alone. And that's the simplified form. Notice I'm writing the piece that I square root goes out front of the messy radical, the one that we leave alone. Is what, 6? It is, yeah, thank you. Okay, 50. Does 4 go into 50? Nope, I'm just going to scoot this list down. Okay, 4 doesn't go into 50. Does 9? No. Does 16? No. Does 25? Yes. Okay, so we're going to write square root of 25 times square root of 2. Square root of 25 is 5. And then we just leave the root 2 by itself. Okay, 28. Does 4 go into 28? Does 4 go into 28? Yep. So because 28 is kind of small, like we know 9 doesn't go into 28, or at least we should know that, and then 16 is already over halfway. As soon as you get to the halfway point, stop checking. Because again, if we pulled 16 out of 28, here's what we'd be left with. So we'd say 28 divided by 16, and that's 1.75. Like, we're not going to leave that underneath of a radical. So once you get to halfway, stop checking. So this one is square root of 4 times square root of 7. Square root of 4 is 2. So 2 square root of 7 on that one. And then 72. Does 4 go into 72? Yeah? But it seems like because 72 is kind of bigger that there's probably something a little bigger that might work. So how about 9? Does it go into 72? Yep, 9 times 8. 16, does it go in? 16 go into 72? No. 25 doesn't. Does 36? Yeah. Okay, just to remind you, I just want to do this one slightly different. So let's say you didn't realize that 36 goes into 72 and you decided to do 9, which is fine. So square root of 9 times square root of 8, that's equivalent to square root of 72. Okay, square root of 9 is 3, and then we have square root of 8. But square root of 8 still has square rootable numbers as factors. In other words, I'd have to go back through my list and say, does 4 go into 8? Yeah. Does 9? No, but 4 does. So I would have to split this into square root of 4 times square root of 2 with that 3 out front. And then square root of 4, of course, is 2. And we just end up with 6 root 2. So you can do it piecewise, like work through repeated steps instead of just doing it once. If you happen to notice that this is also the same as square root of 36 times square root of 2, and then you just do one step to the same result. So let's go ahead and check your homework, but let's see, there were 1, 2, 3, 4, 5, 6, 7. Hold up how many you got correct out of 7 on that warm-up, please. All right. In terms of checking, why don't you go ahead and grab your homework page while I pull it up here. So some of these are going to be similar to what we did. Go ahead and just take a second to check. Make sure you got each one all the way simplified. Any of these you'd like? You said 13, right? Okay, so 13 and 15. Let's go ahead and do those. Okay, here's a little hint. If you see the number ending in a 5, there's a good chance that 25 might work, especially if it's big, like 125. So split this into square root of 25 times square root of 5. And then square root of 25 is just 5. Okay, same thing with the 175. So this is number 15. So I see, hey, it ends in 5, and that probably means the 25 will be a factor. But this time it's 7 under there. Okay, square root of 25 is 5, and then we have root 7 left over. Any others that you'd like to ask about on there? Did you have time to check them all? Okay. So when do we do this? Like, why are we learning how to simplify radicals? That's what this process is called. Well, we've done a little bit with the Pythagorean theorem. So when you're using it, you can use simplifying, especially if the directions say no messy decimals or some version of that. Also, this is kind of previewing a little bit of what you'll need to do for Algebra 2. Any questions on it? Cool. All right. Today we're going to talk about isosceles and equilateral triangles. So grab your notes, but I do want to do a quick review problem before we do that. And it will cover the, the triangle inequalities theorem. So go ahead and take a couple of minutes, solve for x on this one. Yeah. Solve for x, directions, and ST. All right, so this is, if you're not told this in a problem, which you probably won't be, by the way, we'll have an assessment on this coming up next week after we do isosceles and equilateral. This, simplifying radicals, classifying triangles, isosceles and equilateral solving, and some similarity stuff. Or excuse me, not similarity, but congruent figures. So I'm hoping that you're studying. I know you had the break, but get back into reading your notes, going back through and studying stuff for this unit. So just a reminder of where to find this. We did 2 examples of this. We talked through them or reviewed them briefly yesterday. So these are in your notes. One was just with x and 2 numbers. The other was with expressions, kind of like the one we have right now. And this is the triangle inequalities theorem, where we're going to write 3 different inequalities and then solve each one and find a range of values for x. So like I told you yesterday, I always start up here at the top left. That's just preference. It's not required to do that. So x, remember this is saying that 2 sides have to add up to be longer than the third. That's all this says. So x plus 3x minus 2, that's 2 sides have to be bigger than the third side, in this case 18. Okay, now we go on around. So now we come and start with 3x minus 2. Add that to 18. And that has to be greater than x. So I picked those 2 sides greater than this side. Now I'm going to do these 2 sides greater than the final side. So 18 plus x greater than 3x minus 2. Okay, it kind of sets up 3 sort of like equations that we have to solve. So over here, we'll combine our like terms, get 4x minus 2 greater than 18. And then add the 2. And divide by 4. And we'll get 5. So divide by 4 on each side. Okay, so that one seems reasonable. Remember, one of these will yield a nonsense answer. That one seems pretty good. Okay, over here, combine those 2 like terms, and we'll get 16. And then when we go subtract this 3x, it's probably, hopefully it's starting to look like, that one looks suspicious. So when I divide by -2, okay, first of all, remember when you divide by a negative, you've got to flip the inequality around. So I'll get x and -8. But can we have negative x values in this problem? Like, can this left side up here be negative? Is that okay? So this is saying that it could be, right? Like -7, -6, etc. All those values, that one's saying would work, and they don't. So this is our nonsense result. We'll kick it out and move on. Okay, next one. Subtract x, add 2, and we'll get 2x and 20. Divide by 2, and we'll get 10. Okay, keep in mind we read these from the variable. So what does this one say? It's pretty normal. X, good, is greater than 5. What does this one say? Read it from the variable. X is less than 10. So if you put those together, x has to be bigger than 5, but less than 10. Okay? So remember our structure looks like this. Put x between two less than signs, and then write the small number, then the big number. And that's a range of acceptable values for x. Now I said, what is st? How do we solve for that? Is there just one value of st that will work? No, there's infinite values, in fact, because between 5 and 10 are infinite different values that would work for x. But we could plug in and get a range. So the range of values for st would be 3 times 5 minus 2 and 3 times 10 minus 2. I did my parentheses weird on this one. Okay, so we get 13 and we get 28. So st is between 13 and 28. So think back to that kitchen work triangle. That would set, hey, that third range, maybe it's your distance to your fridge or something. Could be 13 and then 28 feet. Now, those were too big, the 28, but that's the idea behind this. How'd you do on that after about a week? Give me a thumb somewhere on that one. Okay, you'll have one like that on this assessment, so keep studying this stuff. You've got to look over your notes. You've got to keep familiar with stuff. We'll come back. Maybe I'll save this one for another day. All right, speaking of notes, go ahead and grab those, and let's get into isosceles and equilateral solving. We've mentioned these a little bit before, but now we're going to use them specifically. So let's just go ahead and enter some of that into the notes. Kind of a weird word. So isosceles triangles. Do your best to draw one that looks like two of the sides are equal. I'm going to do that just a little bit better. And the third side is shorter. So something like that. So an isosceles triangle has two congruent sides. Remember our congruent notation, the tick marks tell us that they're congruent. And then also two congruent angles. And those angles are specifically opposite of the congruent sides. So in our picture, it would be these two that are congruent. So opposite meaning kind of across the triangle from those. So you can kind of visualize maybe how we could use this to solve. Maybe we are given this top angle and asked to find some x or something about these bottom two angles because we know they're the same. Also, just to remind you how many degrees are in the triangle overall, 360 or 180, excuse me. Okay, we could maybe use them to solve for x's with the side lengths. Or what you're going to see is that these pictures will be combined with other pictures. So you'll combine properties of an isosceles triangle with properties of an equilateral triangle, etc. Okay, here's another theorem for that one. Called the isosceles perpendicular bisector theorem. What does perpendicular mean?
Intercept
90 degrees, yeah, so. Okay. So we have our isosceles triangle. If we have a perpendicular bisector, so let me zoom this up. So isosceles, because the two sides are congruent. Isosceles perpendicular bisector, because we have this green bisector that is splitting the opposite side in half, and it's also at a 90-degree angle. If all of that is true, then these two angles are congruent. Those two angles are bisected. Okay? So let's kind of make a list of the different properties. So we call that the base. Even if it's not on the bottom, we still call it the base. So it splits the base in half, which means congruent segments. It also forms two what kind of triangles?
right triangles.
Yeah. That angle that is bisected is called the vertex angle. It will not always be at the top. It's just the one that is not congruent because of the isosceles triangle. So the vertex angle is bisected. That one up there at the top. Okay, so this, once we start adding all this in, it allows us to copy and paste some things. That allows us to solve in all sorts of ways. So basically what we just wrote was what an isosceles triangle is, and now you know that it has two congruent sides, two congruent angles. But if we happen to have a perpendicular bisector in that isosceles triangle, it causes that vertex angle to be bisected, as well as the base to be bisected. If you need to be reminded what bisected means, it means two congruent halves. And we marked that. If you copied my picture, you marked that. So that's isosceles. Equilateral, what does that mean? So this is going to have all congruent sides. We'll draw this in a second. And all congruent angles. Does anybody remember what we said about the measure of those angles since they're all the same? Why? Yeah, since we have 180 divided by 3 congruent things. So these are all 60 degrees. So this time when you draw your triangle, try to draw it where all sides look the same length. Mark that they're all the same length by putting the same tick marks on all sides. Mark that they are all congruent angles. Let me change the color on that. And that they're all 60 degrees. This is like the prototype triangle. Like if you think of the perfect triangle, it's the equilateral one. So again, you will see these figures combined, like a isosceles next to an equilateral, and you're going to have to just use these properties to solve through and get pieces that we are asked to find. And I'll show you that in just a second after everybody gets this written down. So keep these notes handy because we'll reference back and forth as we work through our examples. Okay. Maybe we'll come back to that one. Let's do one of these. Okay. So just follow along. You can write these if you want or tell me if you need one in your notes. But basically, we're just using the properties that we just wrote. So this first one says, what's the value of x? Well, first thing you have to identify is what am I working with? Like, it's a triangle, okay? So what about it? Are we dealing with side lengths or angles? What do you think? These are angles, okay? So name 2 things you know about angles in an isosceles triangle. Yeah, that's the thing. Okay, so note that this tells us that this is isosceles. Okay, both of those. So we know it's isosceles, so what's true about the angles? Somebody else. What can you do with the angles that are called out? Like, meaning called out by 5x plus 9 and 28. What can I do with one of those things in order to solve for something else? Nathan, how about you? Mason, how about you? Ryan, how about you? Peyton? Well, what do we know about isosceles triangles? Go read your notes again. You probably don't need that right now, do you? What do we know? Go read your notes. We wrote 2 things. One of them had to do with angles. The other one we've been talking about for 2 months. What do we know about angles in an isosceles triangle? Ezekiel, how about you?
There's 2 congruent sides.
I said angles. What do we know about angles in an isosceles triangle? There's 2 congruent angles. So which is the congruent angle here? Or which 2, I should say, are the congruent ones? Thank you, Olivia. Which 2 angles are congruent? Like, do I copy paste the 5x plus 9 or copy paste the 28? How do we know? It's opposites of these congruent sides, right? So this angle and this angle are congruent. So copy paste your 28. Okay, now how do we solve for x? Like that didn't finish the problem. It just got us to be able to solve or finish. Amaya, how would you solve this? Okay. And yeah, good. She said add them all together, set them equal to 180. Okay. So I feel like you can probably solve this on your own. I'm not going to do that, but we're just talking setup. Okay, how about this one? What's the value of x? What kind of triangle is it? That should be your first question. What kind of triangle is this one? How do we know it's isosceles? Not parallel. Congruent sides, right? So those markings are telling us that these are congruent. All right, how do we solve for x in this one? Well, now we know it's isosceles. We got to take our isosceles properties and apply them. Isaac, tell us. All right, so he knows that since this is isosceles, these two angles are congruent. Therefore, in this one, completely different setup, we set those two equal to each other. Okay, so just zooming out here, I want you to note, think about these as two test problems. They're both isosceles triangles. The setup is completely different. One we had to add up to 180, the other we set equal. And it's not just random, right? There's a reason for each one. So it's really, really important that we know what's going on here. That slide got cut off for some reason. Okay. In triangle ABC, measure of angle A is 20. What are B and C? So measure of angle A goes here, 20 degrees. Ryan, how do we solve for B and C? Okay, we'll start with this question. What kind of triangle? How do we know? What's true about isosceles triangles? Ryan? Okay, so which angles are congruent? B and C. Aldo, how do we solve for B and C? Well, it's not a bad idea. We just don't know what we're adding. Mason, help him out.
180 minus 20 divided by 2.
Okay, here's what he said. Let's call these both what we're solving for, since he said divided by 2, implying that they're the same thing, which is true. They're congruent. So let me show you where he got that. And Aldo said add them up, but specifically adding up to 180. Okay, so we're saying, hey, x and x, those two are congruent, so call them the same variable. X plus 20 is 180. Okay, subtract 20 from both sides. And of course, on the left, we'll get 2x, and then divide by 2. Okay, so he said 180 minus 20. There's that right there. And then divided by 2, because those are the same size. Good job. Okay, you guys try this one. Maybe 2 minutes on this second one. Through this one. First question is what? So what kind of triangle is it? It's isosceles. How do we know? Yeah, in this case, it's showing that because of these angles instead of side lengths. But because the angles are congruent, we know that what else is? Okay, these two sides that are opposite of the two congruent angles are also congruent. Okay, so we have two congruent sides. What does that mean in terms of solving for x? Like, here's a common mistake. Do we add all these up and set them equal to 180? That's a common mistake because these are side lengths. They have actually nothing to do with 180 at all. So, do we add them up and set them equal to something else? No. Okay, so since those two side lengths are equal, we'll set x plus 20 equal to 8/3 x. Okay, we're in algebra mode for a second. How do we solve that equation? You have a number of options. Lewis, what would you do?
I would get the 8/3 into 1 number.
To a whole number? How would you do that?
Divide 8/3.
Okay, but that's not a whole number, right? That's
Or
2.666. Which makes it a decimal, and we're still kind of in the same place. For some people, that might be helpful. It's okay to do it that way. Any other ideas? Okay, here's what he said. Multiply this side by 3. These cancel then, and we're left with 8x. What do you think? Is that okay? Can I just multiply one side by 3? Okay. So now I got to do this side also by 3. Make sure you do the whole side. That's why I'm putting brackets around it. And we'll get 3x plus 60. Okay, that looks better. Now what? So get our x's together, divide by 5, and we'll get x equals 12. Okay, the question actually asks what are the lengths of all three sides. What would we do to figure that out? Yeah, just go up here, plug 8 times 12 over 3, 6 times 12 minus 12, and 12 plus 20. Okay. So that was an example if you compare that one to the last few. So we solved for angles there in that first one, and we solved for angles in those two. This is the first one where we solved for side lengths, and we had to have the notation that told us the angles were congruent. All right, a couple more examples. I think I'll save that one for another day. Here's the isosceles perpendicular bisector theorem that we talked about. Just a little bit better picture than mine. Note that the two sides are congruent, so that's isosceles. And then this line is perpendicular, therefore it bisects. So the bottom has two congruent pieces, and then the two angles on the vertex are also congruent. Lots of congruence in that one. All right, equilateral. Here's those combined kind where we have triangles next to triangles. At least that's the best way to think of it. If measure of angle CBD is 130, what is the measure of angle BAD? Well, where is angle CBD? Like, I remember just recently we had an issue with naming angles. So remember that the middle letter is the vertex, meaning it's the corner, it's the actual angle. So B, that's this whole thing, angle CBD. Start at C, go to B, then to D. I'll do that one more time. C to B, B to D. And then our angle is that one that I marked with red. Everybody good on that? Okay. So that whole angle is 130. And it says find the measure of angle BAD. Alexis, which one is that? Okay. And which angle? That's the triangle. Which angle is BAD? Yeah. Well, this symbol means angle, right? So yeah, it's up here. It's that one. Okay. Vertex is the actual angle. Let's just draw one angle. So B, A, D. That right there is the vertex. So it's like the pointy part, maybe you could say. Does that make sense? Okay, and so the middle letter is always that point. So angle BAD, let me put this reminder. Angle BAD is that one right there. Just on the right side of the line. Okay? That one. All right, well, how do we do this kind then? What kind of triangles are we dealing with? Yeah, do you guys see the left triangle equilateral? The right side triangle is isosceles, so we can't assume that AD is also congruent. So what do we know about angles in an equilateral triangle, Isaac? Okay, let me get this pink thing out of the way. So that whole thing is 130. But he's telling us that this part right here, let's just write it in there, is 60. How did he know that that was 60? Morgan, how about you? Why did he know that angle CBA, right there where I wrote it, is 60? Actually, we knew it was 60 even without the 130. How? Okay. Aldo? Nope. Good job for thinking of that one, that good old friend of ours, linear pair. But note that these two don't make a straight line, right? They just make a line, well, sort of. Why do we know that that angle is 60? It's an equilateral triangle. All angles, always and forever, in an equilateral triangle are 60. Okay? All right, what does that mean that this angle is right here? Okay, 60 and this angle have to add up to the 130, right? So we're using angle addition postulate, so that makes this 70. Okay, how do we get angle A? Well, angle BAD. How do we get that one? Peyton, how about you? Think about it like you do know. If we know this is 70, we know this is isosceles. How do we get angle A? Angle BAD. What's true about this angle over here? Peyton? It is. It's equal to BAD, right? So we could, if we wanted, mark that and that as congruent. And we know this one is 70. What do they all three add up to? 180. So this is like x plus x. So x plus x plus 70 equals 180. And the reason why, again, is those two angles are congruent because this is equilateral. We got the 70 from subtracting 60 from 130. All right, 2x. Let's go ahead and subtract this 70 over. So 2x equals 110. What is x? 55. Which is angle BAD, okay? All right, you guys try this one. Note your types of triangles that are stacked together there. And we're trying to find angle U, that's this one over here. And let's take a couple minutes on that one. Okay. What kind of triangle is the left one? Okay, so this one is isosceles. We know that because of the two single tick marks. And 72 is the vertex angle. So these two angles are congruent. So hopefully by now you've seen that in this, it's okay to redraw this if you want to. Put the 72 there and call those congruent. And hopefully you're seeing this pattern with these. We know it's like 2 of the same plus that third angle adding up to 180. Okay, so we get 2x plus 72 equals 180, and then 2x equals 108, and x equals 54. Okay, so this angle right there, angle SVT, is 54 degrees. Okay, now what? Okay, let's use, I think it was Alder who said this. What kind of situation is that right there? Linear pair. So those two add up to 180. Okay? So this one is 180 minus 54. Okay, so now we know if we redraw this triangle, by the way, that's a good strategy. We know this top angle is 126, and now we know that these two are the same because that second triangle is also isosceles. I'm calling it Y because we don't want to use the same letter as we did before for the other one. Okay, so 2y plus 126 equals 180 in that triangle. Subtract 126 and get 54. Divide by 2 and you get 27. Let me label that measure of angle U. Okay, so it's just kind of combining either isosceles angles, equilateral angles. We included a linear pair here. Definitely keep that 180 in mind, but it's not only what you use. And you just kind of work your way from one point to another. It's just chaining your thinking as you work through. I think that's probably good enough. Yep. So your work from now until next Monday is to complete this sheet. So the whole thing, all the problems. And you have still 22 minutes or so. So please work till the bell and ask questions. Make sure you're getting this. This is that opportunity to get clear on everything.